Hello, everyone. Thank you for joining one more lecture of our Processing in Memory course. Today, we have Nika Mansouri Ghiasi, who is a PhD student in the Safari Research Group, and she's going to introduce this interesting work on in-storage processing for genome sequence analysis. Nika, whenever you're ready, please feel free to go ahead.
Okay, thanks, Juan, for the introduction. Okay, so hello, everyone. I'm Nika, as Juan mentioned, and today I will introduce GenStore, a high-performance in-storage processing system for genome sequence analysis. Genome sequence analysis is critical for many applications, such as personalized medicine, outbreak tracing, and evolutionary studies. Genome sequencing machines extract the smaller fragments of the original DNA sequence, known as reads. Read mapping is the first key step in many genome sequence analysis applications that aligns reads to potential matching locations within the reference genome. And for each matching location, the alignment step finds the degree of similarity between read and the reference by calculating the alignment score. Calculating the alignment score requires computationally expensive approximate string matching, or ASM, to account for differences between reads and the reference genome due to sequencing errors or genetic variation. And based on this genetic variation, actually, we can make conclusions about the state of the data sample that we collected, if it's like for personalized medicine or other applications. So these differences are very useful for that sense. So read mapping performs this expensive alignment computation on large genomic datasets containing millions of reads. Therefore, read mapping is both computationally expensive and incurs high data movement overhead from storage. There has been significant effort into improving read mapping performance in different parts of the system, such as computation, near caches, and main memory, through either efficient heuristics or hardware accelerators and various filters that prune reads that do not require expensive computation. While these approaches address the computation overhead in read mapping, none of them alleviate data movement overhead from storage, whose impact becomes even larger when the computation overhead gets alleviated. Our key idea is to filter reads that do not require expensive alignment computation in the storage system to fundamentally reduce data movement overhead of read mapping. Examples of reads that do not require this costly alignment step are exactly matching reads to the reference genome that do not need approximate string matching performed during alignment, and non-matching reads that have no potential locations in the reference genome, and therefore they can skip the alignment step. However, filtering reads in a modern SSD can be challenging due to different behavior across read mapping workloads and the limited hardware resources in the SSD. By addressing these challenges, we propose GenStore, the first in-storage processing system designed for genome sequence analysis to reduce both computation and data movement overhead. GenStore provides high performance and energy benefits compared to state-of-the-art hardware and software baselines. So that was a summary of my talk. So let's start with the background on read mapping so we can dive into the talk in more detail. Mapping reads to reference genome requires expensive computation on large data sets, and the search space in the reference genome can be very large. For example, the human reference genome contains more than 3 billion characters. Therefore, mappers typically use an index of the reference genome to reduce the search space. This index contains unique K-length subsequences called K-mers extracted from the reference genome and the locations of these K-mers in the reference genome. Read mapping is a three-step process. The state-of-the-art read mappers involve several heuristics to reduce the cost of expensive alignment computation. In the first step, called seeding, the mapper determines some potential matching locations or seeds in the large reference genome where the read could map. To do so, the read mapper extracts K-mers from each read and looks up the K-mers fetched from a read in the reference index. For all the K-mers that hit in the index, the read mapper marks the locations of them in the reference genome as reads potential matching locations or seeds. So basically, these are the locations in the reference genome that the read potentially might match. To further reduce the cost of computationally expensive alignment, the read mapper performs a second step called chaining or seed filtering, in which the mapper prunes the seeds in the reference genome to which the read would not align, using a simpler approximation of the alignment score. At the end of this step, the reads that have all of their locations filtered skip the third step, but for the remaining reads, the third step, which is the costly alignment step, determines the exact differences between the read and the reference genome via approximate string matching operations. So we perform experimental studies to understand the potential of efficient in-storage filters for improving read mapping performance. We perform a case study on a real-world genomic data set on various read mapping systems and state-of-the-art SSD configurations. And we make several observations. First, the ideal in-storage filter significantly improves performance by reducing computation overhead and data movement overhead. Second, filtering outside SSD relatively provides lower performance benefits since it does not reduce data movement overhead from storage, and it must compete with read mapping for system resources such as main memory bandwidth and computation resources in the host system. So a hardware accelerator reduces the computation bottleneck, which makes I/O even a larger bottleneck in the systems and makes the and emphasizes the necessity of in-storage filtering even further. Motivated by these observations, our goal is to design an in-storage filter for genome sequence analysis in a cost-effective manner. We have three key objectives in designing our new system. First, the system should provide high in-storage filtering performance to overlap the filtering with the read mapping of unfiltered data. So wherever the read mapping system is located, either is like in a PIM system, in memory system, like in main memory or like near caches or an accelerator or in host CPU, this in-storage filtering should be integrated with it such that the filtering operations that happen concurrently in the storage system would overlap with the read mapping of unfiltered data. Second, the design should support reads with different properties and different degrees of genetic variation. Third, it should not require significant additional hardware overhead. So to this end, we propose GenStore, which is the first in-storage processing system designed for genome sequence analysis. And our key idea is to filter reads that do not require alignment inside the storage system and send the unfiltered data to the host system for further processing. However, filtering reads in a modern SSD can be challenging due to different behavior across read mapping workloads and the limited hardware resources available in the SSD. Let's take a look at filtering opportunities based on input read sets. Sequencing machines produce one of two kinds of reads. Short reads that are highly accurate but short, for example, up to a few hundreds of DNA characters, and long reads that are less accurate but long, for example, from hundreds to millions of DNA characters. Based on these, we leverage two filtering opportunities. First, we can filter exactly matching reads, which are reads that match exactly to one or more subsequences of the reference genome and do not require approximate string matching during alignment. Exact matches can frequently occur in short read sets with low sequencing errors and low degree of genetic variation. Second, we can filter non-matching reads. Such reads do not have any potential matching locations in the reference genome and can skip the expensive alignment step. Non-matching reads can frequently occur in long read sets with high sequencing errors and short or long read sets with high degree of genetic variation. So by thorough analysis of mapping process of reads with different properties and different degrees of genetic variation, we designed two low-cost in-storage filters, GenStore EM for exactly matching reads and GenStore NM for filtering most of non-matching reads. Let's take a closer look at GenStore EM. GenStore EM accelerates read mapping by using an efficient in-storage filter to filter reads that have at least one exactly matching location in the reference genome via simple operations and without requiring alignment. The key challenge in designing GenStore EM is the large number of random accesses to large data structures inside the SSD. This is challenging because NAND flash memory exploits poor performance for random access reads, and there is limited DRAM capacity available in SSD, which is relatively small compared to the size of data structures that need to be randomly accessed. So to reduce the number of accesses per each read, we introduce concept of read-sized k-mers. Therefore, instead of extracting several k-mers per each read and performing index lookup for each of them, we can use the whole read as one k-mer, so basically a read-sized k-mer, and have only one index lookup per read. And to avoid random accesses to the index, we introduce sorted index of read-sized k-mers. Since we know for each read we will only have one access, we can already sort the index so that we can sequentially access these. So this sorted index allows finding exact matches via sequential scanning of the read sets and the index. I showed a key idea of GenStore EM with a simplified example in which each short read consists of 10 characters. Suppose that we have two data structures, a sorted read table, each entry of which stores a read and its unique ID. So here a read is 10 characters, but as I said, short reads can be few hundred characters. So in this table, we have sorted read table. So each entry of it is a read and its unique ID. And second, we have sorted k-mer index, which contains all unique read-sized k-mers extracted from the reference genome, along with each k-mer's corresponding location in the reference genome. And each data structure is sorted by read and k-mer in alphabetical order in this case. So we sequentially scan through these data structures in 3 different ways based on a comparison result of current read and k-mer. First, when the current read and k-mer are identical, we record the read as an exactly matching read that can be filtered from further read mapping process, and then we move to the next element in both arrays. So if the read is alphabetically larger than the k-mer, we conclude that the k-mer does not match any read and go to the next element in the index so we can examine the next k-mer. And finally, if the k-mer is alphabetically larger than the read, we conclude that the read does not match any k-mer in the index and needs to be sent for a full read mapping process. And then we go to the next element in the sorted read table so that we can examine the next read. So using this technique, GenStore EM avoids random accesses and performs filtering using only simple low-cost logic. Despite the key benefits of sorted read-size k-mer index, this index takes up large space because now each k-mer is much larger. So for example, for a human index, it will be around 126 gigabytes. So that happens due to a large number of unique read-size k-mers. So we further reduce the overhead of GenStore EM by replacing the read-size k-mers with the strong hash value of each read that can act as both sorting criterion and fingerprint of each entry. Using strong hash values instead of read-size k-mers reduces the size of the index by 3.9 times. While this index is still larger than a baseline k-mer index using conventional read mappers, our proposal is feasible for in-storage processing due to large capacity and high internal bandwidth of modern NAND flash-based SSDs. Now I show the overall operational flow of GenStore EM with sorted read table and sorted k-mer index in the NAND flash memory, distributed across all channels and dies so that we can leverage the full internal bandwidth of the SSD and the comparator logic on the SSD controller. GenStore EM consists of 2 steps. Step 1 reads the 2 data structures from NAND flash chips to the SSD's internal DRAM in a batched manner. So we would only need the small batches, a few hundred megabytes in the DRAM to stream through these sorted read table and sorted k-mer index. And Step 2 performs exact match filtering within each read batch using simple comparator logic. And in the end, sends the non-filtered reads to the host system for full read mapping. Step 1 and 2 are performed in a pipelined manner, and during filtering, GenStore EM can already send unfiltered reads to the host system to do full read mapping, so the filtering operation and read mapping of unfiltered reads for different batches can happen concurrently. So now let's take a closer look at GenStore NM. Using using chaining, GenStore NM filters most of the non-matching reads, which are reads that would not align to any subsequences in the reference genome. Recall that chaining filter calculates the similarity score for each read, called chaining score, and filters reads with no high scoring potential matching location. Calculating a chaining score in SSD is challenging because finding the best chaining score requires performing many iterations of a dynamic programming algorithm for all seeds within a read, and this is particularly challenging. So basically this iteration happens for every seed, and that can be challenging for long reads since they have a large number of k-mers per read. So to reduce the cost of chaining, GenStore NM uses a lightweight chaining filter that selectively performs chaining on linear reads with small number of seeds and directly sends reads that require more complex chaining to the host system. This idea is based on our observation from analyzing a wide range of real-world genomic read datasets. And this figure shows an example. So it shows an alignment probability of a read in a long read dataset to subsequences in a reference genome as a function of number of seeds per read. We observed that reads with sufficiently large number of seeds are likely to align to subsequences in the reference genome, and such reads can be directly sent to CPU for full read mapping, bypassing the in-storage filter. Because in the end, even if they go through the filter, with a high probability they won't be filtered, and they need to, in the end, be sent to the host system for full read mapping. So we conclude that the selective lightweight chaining approach can filter many non-aligning reads without costly hardware resources in the SSD. For more detail on GenStore NM, please refer to our paper. So now I will go into our results. We evaluate the following systems: BASE, which is a state-of-the-art software or hardware read mappers for both short and long reads, and GS, or GenStore, is base integrated with GenStore inside SSD. So basically, we would see each of these baselines, how much benefit GenStore introduces to them if it gets integrated with them and concurrently filters some reads inside the SSD, while each of these baselines are performing read mapping in the system. And we evaluate these mappers and systems with various SSD configurations, a low end, a medium end, and high end SSD. And for other details about our methodology, please refer to our paper. So we analyzed the benefit of GenStore EM for a 22 gigabyte short read set where 80% of reads exactly match some subsequences in a reference genome and can be filtered. We show the benefits of GenStore on software and hardware read mappers. And GenStore provides up to 2.5 times speed up compared to software baseline and up to 3.3 times speed up compared to the hardware baseline. GenStore provides an average 3.9 times energy reduction. So we analyzed the benefits of GenStore NM for a 12 gigabyte long read set with very high genetic variation compared to the reference genome, where 99.7% of reads do not match any subsequences in the reference genome. We show the benefits of GenStore on software and hardware read mappers and show that GenStore provides up to 27.9 times speed up compared to software baseline and up to 19.2 times speed up compared to hardware baseline. And it also on average provides 27.2 times energy reduction. So we find area and power values of GenStore by synthesizing GenStore EM and NM using 65 nanometer technology node, and find that for an 8-channel SSD, the area of GenStore is 0.2 millimeters square and the power is 26.6 watts. By scaling the area to lower technology nodes, we observed that the area overhead of GenStore is 0.006% of an Intel processor and less than 9.5% of the 3 ARM processors in a SATA SSD controller. Let me briefly talk about other results that are included in a paper before concluding this talk. So these results include the following: effect of read dataset features on performance, such as its data size. So for example, we analyze input data sizes up to 440 gigabytes, and filter ratio, basically how many % of reads in a read dataset can be filtered, and performance benefits of an implementation of GenStore outside the SSD. We show that in some cases, it provides performance benefits due to more efficient streaming accesses, but it provides significantly lower benefit compared to GenStore inside SSD. And we also provide a more detailed characterization of non-matching reads across different read mapping use cases and species. Now let me conclude by giving the summary. There has been significant effort into improving read mapping performance through efficient heuristics, hardware accelerators, and various filters that prune reads that do not require expensive computation. While these approaches address the computation overhead in read mapping, none of them alleviate the data movement overhead from storage, whose impact becomes even larger when the computation overhead gets alleviated. Our goal is to improve the performance of genome sequence analysis by efficiently and effectively reducing unnecessary data movement from the storage system. The key idea is to filter reads that do not require the expensive ASM computation in the storage system to fundamentally reduce data movement overhead. However, filtering reads inside SSD is challenging because first, reads mapping workloads can exhibit different behavior. And second, there are limited available hardware resources in the storage system. To this end, we propose GenStore, the first and storage processing system designed for genome sequence analysis to reduce both computation and data movement overhead. GenStore provides high performance and energy benefits compared to state-of-the-art hardware and software baselines. So, as you've seen, this talk was, this project was intersection of genomics and storage processing and near data processing in a sense. So I would like to briefly talk about two Safari PNS courses on genomics. So genome sequence analysis on mobile devices and accelerating genome analysis with FPGAs, GPUs, and new execution paradigms. You can find the links on my slides by clicking on these, and also on courses tab in Safari web page. So yeah, thank you very much for listening to my talk.
Thank you very much,
Sure.
Nika. Thank you very much. Very good talk.
Thanks.
I don't see any questions in the chat, but I would like to ask you a couple of things.
Sure.
So you mentioned that in the paper you have included evaluation of GenStore on different devices.
Different device? You mean storage devices or?
No, I mean you said outside the SSD.
Yeah.
So that's on a CPU.
Oh, so for software baselines, we assume this is running on the CPU. And for hardware baselines, we assume that GenStore hardware components are running in like an hardware accelerator working in parallel with the hardware accelerator baseline.
I see. Okay. Yeah, those would be interesting results for sure.
Yeah.
A couple more questions I have is, so something that you need for the EM version of GenStore is the reads are sorted, right?
Yeah.
So where is this sorting happening?
Mm-hmm. Yeah, that's a very good question. So we measure the throughput of sorting for different batches of reads that get generated from the sequencing machine. So, and we compared the because like sequencing machines generate reads in batches. So we can sort and merge different batches. So we measured that throughput with the throughput of sequencing and base calling, and we realized that the throughput of that step is much higher than sequencing and base calling. So it can be integrated within the same pipeline. So we would have sequencing, base calling, and I don't know, this pre-processing. So without changing the overall throughput of, let's say, input data generation. So we envision it to be kind of like integrated as part of the same pipeline.
Mm-hmm. But then maybe the alignment could also be integrated in the pipeline.
Yeah, that is true. But also sometimes you would need to do alignment several times. For example, you want to try with different parameters, different camera length, or different, let's say, thresholds for the alignment operation, or you want to align several a read set against several reference genomes, for example, in the case of, let's say, COVID-19, and then when things are changing and different references come, or for various reasons, you might want to repeat that. So it is always also not possible to definitely integrate it as part of the same pipeline, because you might want to just do it several times.
Mm-hmm. Mm-hmm. I see.
But definitely that is an important use case always, right? Or like an important scenario for runtime analysis.
Mm-hmm. Yeah, I think so. So there is one question in the chat, I think. Yeah, I don't understand the question. I'm sorry. I mean, the question is going to be, Nika, in the YouTube chat. So
okay,
maybe we can later discuss it, or maybe this person can send us an email as well, because that's possible if
Sure.
want to ask something specific. Okay. Yeah, I guess I have one last question is about the slide 31, because you define these two regions for those reads what that will be aligned in the processor. So how frequent is this? I assume that you have like some statistics in the paper.
Basically, how many reads would not align?
Yeah, exactly. So how much data movement are you actually saving here?
It heavily depends on the use case and the degree of genetic variation between the read data set and the reference genome. For example, for humans, because we don't have that much degree of genetic variation, so the opportunity is relatively less compared to some viral samples or bacterial samples that relatively evolve much faster. So we observed, let's say, filter ratios of, I don't know, up to 99+%, while for, let's say, some species, it can be, I don't know, less than 20%. So it heavily varies. And actually, we provide a lot of data about that for different use cases and species. So in the paper, so I think that it would be also nice if people are interested, they can take a look at those analysis. Yeah.
Okay. Thank you very much, Nika.
Yeah, thanks, Juan.
I don't have any other questions. I hope that people enjoyed the talk, and they can also check your paper more carefully to learn much more about this topic.